Good morning all. I'm playing around with retro breadboards again. This was my retro breadboard, this blue breadboard. I bought this from Maplin, I think 20-30 years ago, something like that. This blue breadboard here was my 4-bit binary to hexadecimal displayed on a 7-segment indicator, 7-segment LED display. Now you probably saw this wired up with just messy rat's nest wires like this, but I've since rewired it with, well, these rather weird bits of ribbon cable which I found like this with they're very odd. They've got these kind of tinned but stripped back ends, and they're all about 2 inches long, and I thought, I wonder if I could rewire the whole of this thing with these. So I did. I'm not entirely sure why. I was just watching the internet or something. However, today's video is about this breadboard here, because when you bought these breadboards, you could get these little front panels with them, and they're clearly designed to take, well, potentiometers in these sort of odd-shaped holes. Modern potentiometers being very small are sat right down low in these holes. Possibly toggle switches could fit in these holes as well, but these small holes are 5mm diameter, apart from that one which I seem to have drilled out. So they take LEDs. So today's breadboard is just this front one, and it's a circuit which has potentiometers and LEDs, and it actually works. Look, they switch on and off when I turn the potentiometers. So what this is actually doing is it's driving the LEDs. This is a comparator. It's 4 comparators in a chip. It's an LM339. And I've got a voltage divider here. It's these 4 big resistors. I thought I'd use big resistors so that you could see them. Don't worry about these other 2 resistors. They're just for current limiting on the LEDs. So I've got a potential divider here generating a half voltage, 2.5 volts. And when the pot crosses the threshold at about 2.5 volts, the LED changes state. This one I've wired the other way around so that it's just a bit of fun. That one goes off when you take it left. This one goes on when you take it left. Yeah, a bit of fun. Now this doesn't make a lot of sense, so I'm going to draw the circuit. I'll draw the circuit just of 1 pot and 1 LED so that you can see what this is doing. So this is it. We have a comparator here, non-inverting input and inverting input. Now I think on one of these I did it one way around, and on the other way around. Non-inverting input, I've got my pot. So let's draw it as this symbol. That goes up to 5 volts, that goes down to ground. This is GND. This is 5V. And that goes to the non-inverting input. And then on the inverting input, I've got a potential divider. Oh, let's draw different kinds of resistors just to mix things up a bit. Another resistor there, but they're equal value, so R and R, and they go into the inverting input. Now when the non-inverting input, the positive input, goes higher than this voltage, now these are equal value resistors as I say, so this is 2.5 volts at this point. When the pot goes higher than 2.5 volts, the LED comes on. When the pot goes lower than 2.5 volts, the LED goes off. Now this LM339 has open collector outputs, and for a while I was playing with it trying to turn LEDs on by sourcing current into them. That didn't work because they can't, this output can't source current, it can only sink current. So what you have to do is have your LED sort of up here, and that goes into there. We have a resistor there to current limit it, and so when this pulls low, it turns the LED on. So in fact, I've drawn the circuit probably of this red one because the output is effectively inverted, because when the output goes low, the LED comes on. So if I go low, that's yeah, so the output will be low, LED turns on. If I go up to the 2.5 volt point and go higher than that, the LED turns off, and then on the green one, I think I just reversed the potentiometer and my potential divider. Now, why, I'm sure you're asking, am I messing around with such a simple circuit? Well, because what this circuit actually is an analog to digital converter. Yeah, it's an A to D converter. And so I was thinking, what would be involved in turning this 1-bit A to D converter, where all we really know from the digital output is whether the analog input is below 2.5 volts or above 2.5 volts. What would be involved in making a 2-bit analog to digital converter? How much more complicated would that be? And well, it is quite a bit more complicated because I've had to do all this stuff. But just let's look for a moment at how useful this 1-bit A to D converter is. Well, not very. All it tells me is if my voltage is below the midpoint, which is 2.5 volts, I get a 0 output. Or if it's above 2.5 volts, I get a 1 output. So it doesn't tell me much. Let's draw a graph of this. Voltage here, this is 2.5 volts, 0 volts, 5 volts. If we're in this range below 2.5 volts, we get a 0. If we're above 2.5 volts, we get a 1. That's a 1. I suppose I should mark it there. And that's a 0. It's not very useful. And in fact, this A to D converter doesn't tell us what the voltage is at the input. It only tells us what range of voltages at the input or on the potentiometer, what range of voltage is there. It doesn't tell us the actual voltage. What we really want is something more like a straight line, which would have a direct relationship between the actual voltage and the digital output. But actually, you can never have that. The digital output will only ever tell you a range of voltages that the input signal is in, not the actual voltage. So if we go to a 2-bit analog to digital converter, it will give us more information. It will tell us whether the voltage is between 0 volts and 1.25 volts, or 1.25 and 2.5, or 2.5 and 3.75 volts, or 3.75 and 5 volts. Now the output will be, and I'll do this in a different color, let's see if I can get my Sharpie to work, something for that range and then something for that range. I'm trying to keep this yellow line sort of aligned with the ideal curve here. Another thing for that range, and then another output value for that range. The output values will be 0, 0, 0, 1, 1, 0, 1, 1, or at least they will be if we can get this to provide a binary output. That's actually quite difficult. So in terms of designing this as a circuit, the first thing I need to do is I need to have 3 comparators, because there are 3 voltages, 1.25, 2.5 and 3.75, at which point something changes, the output changes. 0 and 5 volts we can't do much about because we can't go below 0, we can't go above 5 volts, but we can certainly go either side of 1.25, 2.5 and 3.75. So let's draw 3 comparators like so. Now I can do this because each of these chips has 4 comparators, but let's draw 3. We've got a plus and a minus on each one, plus, minus. Now we need a resistor chain with 4 resistors, one here, one here, one here, and one here. So this is our resistor divider chain, and we'll feed this into the negative input of the 3 comparators, and then we'll have a pot again, which will be our continuously variable input, and we'll send that to the positive input of all 3 comparators. It's going to look a bit like that. So just drawing in the remaining VCC and ground points. Now you'll notice that I've actually put 4 resistors in a chain there, mainly because these are quite low value. These were 3.3K, and I didn't want too much current flowing down there, so I used 4 resistors to start with, which is good because I've got that resistor chain already on the board. I've got a pot. Only going to need one pot now. I don't really need two of these comparator circuits, but I do need three comparators. Now, what's going to happen as the potentiometer voltage rises from 0 up to 5 volts? Well, we're going to cross each of these voltage thresholds in turn. So initially, the three outputs of the comparators will all be off. We'll have 0, 0, 0. Then we'll have the first one turn on. So we'll have, well, actually, let's read it from most significant down to least significant. We'll have 0, 0, 1. Then we'll have 0, 1, 1. Then we'll have 1, 1, 1. And that's not binary. And for one thing, we haven't got 2 bits of output. We've actually got 3 bits of output doing this sort of code. Now, I probably should have drawn this upside down. At the bottom voltage range, we're going to have 0, 0, 0 for C, B, and A. Let's call these C, B, and A. Then we go 0, 0, 1, then 0, 1, 1, and then 1, 1, 1. Now, this is not a binary code. This is actually called a thermometer code or thermometer scale code, because we simply get one additional output coming on as we move up the scale. What we're going to need to do is work out some sort of encoding, a digital encoding, to turn this thermometer scale code into binary, 2-bit binary. And this is where it all got a bit complicated, and I had to sort of go back to my digital logic education, Carnot maps. I did the Carnot map wrong because I drew it in binary sequence, and of course Carnot maps have to be done in grey code sequence, 0001, 1110, otherwise you don't get these groupings. You've got to remember that this side of the Carnot map along that edge is joined to that edge. This edge is wrapped around to this edge. It actually, if you fold it all up, it looks like a donut, a toroid. Then you pull out groups. You can treat don't cares as ones. There are lots of don't cares here because there are lots of codes that don't exist. 3 bits would nominally give you 8 codes. Well, half of them don't exist because we've only got 4 codes. So lots of don't cares. You pull out the groupings. One of the groupings there is just C equals 1. So we can put C into an OR gate and the output will go high. Here's the output. Incidentally, this is a Carnot map for the least significant bit. The most significant bit is actually very easy because it's a direct copy of B. So we can just feed the B comparator output straight out as our most significant bit, but our least significant bit has to be coded with a bit of digital logic, and I've come up with its C as a 1 or BA is 0, 1, that group there. Then I kind of decided that an inverter, an AND gate and an OR gate would be a bit of a pain because I'd need an LS04, an LS08, an LS32. So I thought, well, can I use, I don't know, De Morgan's theorem or something, Boolean algebra basically, to turn this into all NAND? And I think I can, but I think annoyingly I need 5 NAND gates. And you get 4 in a package, so I'll need 2 packages to do this all in NAND logic. I think I've got that right. I'm not entirely sure. I'll just build it and see if it works. Right, so in order to turn this into a 2-bit A to D, I'm just going to have one pot. So let's pull this knob off. I've got to be a little bit careful because the little lugs on the bottom of this front panel, you can probably see, are all a bit stressed. One's broken off years ago. So I just want to be a little bit careful that I don't totally destroy this vintage breadboard front panel before I've even started. Right, let's try and get that knob to come off. And then I need my 10 and 13 spanner to get that pot off. That can drop out. The red LED is much brighter than the green one, so I think I'll actually lose the green one. So I don't need those. Now, in fact, I'm going to need, well, initially 3 LEDs, because I think what I'll do is I'll just build this. 3 comparators, the chain of 4 resistors, all the same value, the pot, and I'll just put an LED on each of these, and we'll see what that looks like. So I probably won't use a front panel LED because these take a while to solder and use heat shrink and make them all nice on this front panel. I'll probably just put LEDs on the breadboard, leave the pot there. That's what I'll do. Right, LM339 pin out because I need to get some numbers for these various inputs and outputs. You can see actually I've got two LM339s on here. So I've got a total of 8 comparators. Yes, I'm already thinking 7 comparators for a 3-bit binary output. But let's not do that just yet because things get very complicated. So let's pull one of those out. I'll just use the one chip, get some numbers written down here for these 4 comparators. So I'm writing these down. I've numbered these 1, 2, and 3. 2 plus is 7. 2 minus is 6. Let's put that there actually. 3 plus is 9. And 3 minus is 8. The output of that is right up there, 14. The output of number 2 is right up there, 1. And the output of number 1 is pin 2. Right, let's wire that up with the resistor chain. I need some LEDs with integral resistors, but they must be on another breadboard somewhere. So I'll do red, yellow, green, kind of traffic light style, because I haven't got many of these left. So I'll do them as red, most significant bit. Now remember, this is not a binary scale, this is our thermometer scale. Yellow there, and green I'll do as the bottom one. Okay, let's wire the LEDs up. Right, a couple of things. Yellow LED didn't work, so I've got a red LED in there, so it's red, red, green. Okay, not much I can do about that. The pot is down at its lowest level. It's down near ground. It's at ground. And of course, all LEDs are on because these outputs are open collector. So they, when the comparator turns on, this point pulls low and turns the LED on. So low, low, low is on, on, on. So you have to read these as 0 is the LED is on. So here we have the 4 patterns, 0, 0, 0, 0, 0, 1. Remember, I'm reading this inverted. 0, 1, 1, and 1, 1, 1. Now the logic, when I apply it, this logic will obviously invert the outputs of the comparator and put that in the correct logical sense. And so if we build this logic circuit, we should be able to create the least significant bit of our binary output. The most significant bit is simply B. So all that does is it changes state, the middle LED, at the halfway point. Yeah, that kind of makes sense. Right, so having built the thermometer scale output straight out of the comparators, I now need my logic. I'm going to do this in all NAND logic because that means I can use Sem4LS00s. I've got a couple of those up here. Sem4LS00, Sem4LS00. So let's put those on the breadboard, put power to them, and see if I can build this encoder. Right, while I cut some little pieces of wire to put ground and VCC on these 2 logic gates, they're going to run on 5 volts. That should be fine. These outputs are open collector, so they will pull low to produce a low signal and just not do anything to produce a high. LS logic tends to float high. I could use pull-up resistors, but I'm not going to bother because I don't want to waste extra time. They'll float high enough to just switch over into the high threshold. I think they then just sit there, so they're not very noise immune, but it's probably good enough. So I'm going to hook the outputs of the comparators directly to the logic gates, and I'm just going to try and implement this logic circuit. Now I've decided that my most significant output is just a copy of B, the B output, which is pin 1, but of course I need to invert it. So let's feed pin 1 of the comparator through one inverter and put an LED on the output. That's my most significant bit. Right, the biggest problem here is that my pin numbering is a total shambles, and my chip numbering, I've called this IC1, that's that set of groupings. This is IC2. I've just got myself into a total pickle. Actually A doesn't invert, so that crosses out. It's actually B that inverts, so that goes there. So yeah, you need to invert B with a NAND, put A straight into the NAND. The NAND has an inverted output, that goes into another NAND. There's a NAND there to invert C. There's a NAND to invert the output of the main NAND. Also, for the most significant bit, we've got another NAND here. So in the end, actually, I used 6 NAND gates to turn my 3 input bits into 2 output bits. But guess what? It works! With the pot fully down to the left. Oh, the sun's coming out now. So with the pot fully counterclockwise, anti-clockwise, fully to the left, so it's at ground. We've got 0, 0 as our binary code. As I lift that up, the first code I get is 0, 1. As I cross that center threshold, it goes to 1, 0. And then when I get to the 3/4 point, we get 1, 1. And it's that all the way to the top. So there is my binary coding. 0, 0, 0, 1, 1, 0, 1, 1. It works! It's a 2-bit analog to digital converter. Here's the transfer function. Voltages between 0 volts and 1.25 volts give a 0, 0 reading. 1.25 to 2.5 volts, 0, 1. 2.5 volts to 3.75 volts, you'll get 1, 0. And 3.75 volts up to 5 volts, you get a binary output of 1, 1. Now, what if we want more resolution? What if we want to go to 3 bits of binary encoded output, which will represent 8 different voltage ranges? Well, the first thing we'll need is 2 to the n minus 1. So 2 to the power 3 is 8 minus 1. We'll need 7 comparators. I've got another comparator chip. It's actually there, so I can do 7 comparators. But the problem is the encoding logic to create 3 bits gets very, very nasty, and I wouldn't want to do it with NAND gates. However, there is a chip, it's called the 74148, I believe, which is a priority encoder, which can encode 7 comparator outputs into a 3-bit binary code. So I've ordered one of those because, yes, I actually want to build the 3-bit A to D converter. Incidentally, this A to D converter is not the type that you would get in a microcontroller. This is actually a flash A to D converter because it converts analog to digital in a flash near instantaneously. Typically in microcontrollers, you'll have a successive approximation A to D converter, which takes 2 to the n clock cycles to actually convert. So if it's, say, an 8-bit, it'll take 8 clock cycles to convert. If it's a 10-bit, it'll take 10 clock cycles. But I'm not going to build a successive approximation A to D converter because they're quite complicated. They need a timing system, so you'd have to have a clock and a counter and stuff like that. I'm just going to build a flash A to D, which converts instantaneously. But you can see that the number of comparators rises to the power of 2 exponentially. So if you want an 8-bit converter, you have 2 to the 8 minus 1. You'd need 255 comparators, and that's a lot. But yeah, I'm very happy with my 2-bit A to D converter with my 2-bit binary output representing not actual voltages, because it doesn't. It represents ranges of voltages. So say we have this code 0, 1. We know that we're somewhere between 1.25 volts and 2.5 volts. An analog to digital converter will never tell you actually what the voltage is on the input. It will tell you which ranges it is between. Yeah, result. I'm happy. Cheerio.